All right, I want to give you a couple of examples of operators in action. Ooh, how exciting. Operators in action. That sounds like, I don't know, something that needs Rocky. Oh, Rambo. We need Rambo. Operators in action. Okay, so here's a value, 10, and I'm assigning it to, can you see that? Is that big enough for you? I'm assigning it to value A, and here's another quantity, minus A. And now I'm going to assign C. And C is set equal to tilde A plus 1. So if I print out A, it should be equal to 10. I think we can all agree on that, right? Are we good with that? Yes. If I print out B, which is equal to minus A, one would think that should be equal to minus 10. Does that sound about right? Okay. What do you suppose C is equal to? Well, if you complement and increment, what have you done? Remember your lesson from digital design. It's 2's complement. So if you complement and increment, you invert, right, and then add 1. And what happens when you form the 2's complement? You form a negative number. So if you take 10, invert it, and then add 1, what will the value be? Minus 10. So A will equal 10, B will be minus 10, and C will be equal to B. And that is true. So internally, C, C++, and Java all use 2's complement to represent integers. Isn't that cool? That's a good example. I like that example. You might not have expected digital design to come in useful in this course, but there it is. 2's complement. Sweet, right? Now, what's the difference between bitwise operations and Boolean operations? Well, let's see. We'll do a new one. Let's make a Java class, and we'll call it the Boolean. Boolean versus bitwise. Boolean versus bitwise. So in Boolean versus bitwise, I'll just try and, maybe I should make this larger. It seems like it's too small, doesn't it? I can almost see like going in and I thought there was a preferences setting in here, but I don't remember how to do it. Preferences? Settings, that's it. Code style, Java. I want like bigness. How do I make it bigger? There should be a thing with like fonts. General? No. Where's like the editor? Oh, here it is. And then there should be a thing with fonts. Fonts. And where is the size? Can we change the size? I don't know how to do it. Console font? I don't want that. Alright, we'll just have to live with it for now. If you can't see it, you can get closer or something. So we'll make up PSV M, Control J, Enter, and let's try and do something with a Boolean. So Boolean A equals true. Boolean B equals true. Boolean C equals not B. Okay. Boolean D equals C and B or A. Okay? Those are Boolean operators, and they are all being used in Java in a very standard way. Let's try and do one with bitwise operations. Integer IA equals 90. Suppose you didn't know the hexadecimal version for 90. Let's try another one. How about this? X7F. Does that work? No. Can't do X? Maybe it's OX. OX? I forgot how to do this. 0x. Yes, thank you. Integer IB equals 0x, let's try 1f. Okay. Now integer IC equals IA. Now notice and percent, I only use a single and percent, not two, and then IB. So now what will happen when I say S out, Control J, enter? I would like to see IC in hexadecimal in my print statement. So what I'll do is I'll say something like this: integer dot toString of IC comma 16. And what that'll do is it'll take the integer IC and convert it into the base 16 quantity. Got that? I can use any base up to 36 using integer.toString. So what will this print? You think it'll multiply? And percent is a bitwise and. Bitwise and of 1f with 7f. Now think about it. 7f, that's 1, 1, 1. That's 3 ones. And then f is 4 ones. 1, 1, 1, 1. And you're going to AND that with 1, 1. And then 4 ones. So what will that look like? In binary, we write 7f equals 3 ones, 1, 2, 3, that's 7, and then 4 ones, 1, 2, 3, 4, that's f. Whereas 1f is equal to 0, 0, 0, 1, oops, and then 1, 1, 1, 1. So now if you do a bitwise AND, what do I expect? One ANDed with 0 is 0. And one ANDed with 0 is 0. And the others are all 1. So 1f ANDed with 7f should be equal to 1f. That's what I expect. And it is. So 1f was used as a mask, right? So notice ampersand is a really different operator from ampersand. Ampersand expected Boolean arguments, whereas and% expected scalar arguments that were fixed point. Fixed point scalar arguments, right? Two kinds of primitive data types in Java. Numeric and non-numeric. Two kinds of non-numeric data types in Java. What are they? What are the two primitive data types in Java? Numeric and non-numeric. What are the two primitive data types in Java that are non-numeric? String is not a primitive data type. It is a reference data type.
Boolean and char.
Yeah, Boolean and char. So in terms of numeric data types, there's two different kinds of numeric data types in Java. What are they? Float and fixed point. And there's two different kinds of floating point data types in Java. What are they? Yeah, float and double. And there's 4 different kinds of fixed point numeric data types in Java. And they're 8 bits, 16 bits, 32 bits, and 64 bits. And we call them bytes, right? And for 16 bits we call them short. And for 32 bits we call them ints. And for 64 bits we call them long. And that's it. That's all we get for primitive data types in Java. That's it. And so when you have a bitwise operator like ampersand, it's expecting a fixed point data type. It works with ints, it works with shorts, it works with bytes, and it works with longs. Not in that order. I should have said bytes first, and then shorts, and then ints, and then longs. Going in order 8, 16, 32, and 64. Got that? So let's try it. Byte. Let's pick a letter. BA equals 0x23. Byte BB equals 0x45. Okay. Byte, let's say BC equals BB exclusive OR with BA. Oh, he's having a hard time with that. Why is that?
You exceed the range.
Yes, it looks like I exceeded the range. What if I went and cast it? Oh. BB and BA. No, those are values which should be within the range. Let's see if that's true. BYTE and it says Betty. BYTE and put it in parentheses, and what is that by? Syntactically correct code, which will produce an answer. Can we predict the answer? Sout Control J, enter, integer dot toString of BC, comma 16. What will this print? An exception. An exception. It's going to print an exception. Let's see if we can grok this code. So now let's see. BB in hexadecimal is going to be, I know how to do this. BA in binary. What's BA in binary? 0, 0, 1, 0, 0, 0, 1, 1. Does that sound about right? I beg your pardon?
It's
0, 1, 0, 0. Okay, the 2 part on the left, 0, 0, 1, 0, and then the 3 part on the right, 0, 0, 1, 1.
But isn't 2, 0, 1, 0, 0?
I'm trying to make this as equal to 0x23. 0, 0, 1, 0 is 2.
Okay, no, okay.
Yeah, and now I'm going to do BB, and I'm going to set that equal to 4, which is 0, 1, 0, 0, and then 5, which is 0, 1, 0, 1. And that should be equal to 0x45. Okay? And now I would like to predict the output for BC, and that should be equal to a bitwise exclusive OR. So 0 exclusive OR with 0 is 0. And 1 exclusive OR with 0 is 1. And that'll be a 1, and that'll be a 0. And this will be a 0, and that'll be a 1. That'll be a 1. What's 1 exclusive OR with 1? 0. And so now, what is my answer going to look like? 0 x 6 6. Ooh, the bitwise exclusive OR. How cool. So now let's see if that's true. Yep. Works good. Just what you'd expect. Sweet, right? Yes, sir.
Why did we have to cast that exactly?
Because the Java compiler thought that there might be a chance that the result would lose precision if we set it equal to a byte.
Okay.
But we had to tell the Java compiler that we wouldn't lose precision and to trust us and let us do what we want and shut the hell up. So this is my casting shut the hell up compiler expression. Right? I mean, at the end of the day, I like the idea that the compiler would give us a warning, but sometimes it just needs to shut the hell up. Now, let's assume that I said to you byte BD is equal to byte BB, inclusive OR, bang, that's not bang, that's just a bar, bar, oh, I guess I need parentheses, BB bar BA. I'm trying to make something that's roughly parallel to our exclusive OR operation. So now, what do you suppose S out control J enter integer dot toString of BD will print when we print out the 16-bit quantity? Is that right? 6? Yes, 6, 7. That is exactly right. Yep. Cool. How about that? Pretty sweet, right? So now you can do bitwise operations in Java. What do you think? Good, right? Now, let's get a little shifty and tricky. Shifty and tricky. Suppose I then said BD, oh, I know, let's do BC. Byte BC, BC equals BD, shift, 4. Ooh, he's having a problem with that? I got BC. I don't want BC. I want BC, BD, BCD, E, BE. Oh, now he's giving me a problem.
What is that?
This has to be of byte type, and I need to cast. This is the shut the hell up compiler thing. Let me do what I want.
What is that?
So right hand greater than signs means shift to the right, and the number of bits that you shift to the right is 4 bits. So this is a bitwise operation that's telling you to essentially divide by 16. That's 2 to the 4. And so what it's doing is it's going to remove the least significant 4 bits and give us the most significant 4 bits. And so instead of having 6, 7, the answer will be 6. And we can print it. And what I'll do to print it is I'll copy this because I got tired of typing it. Paste it in, and I'll put BE in there. This kind of bit flipping is so useful when you're writing device drivers. Because a lot of times device drivers respond to individual bits that allow them to do certain things. Like you could have data direction registers where each port can be either an input or an output port. And you could have each bit mapped differently. And you'd have to write a whole series of 1s and 0s. So shifting is part of what I would call bitwise operations, but there's shifting, it can go the other way too. Suppose we said BE, A, B, C, D, E, F, BF is equal to BE, shift, shift, with a difference, and the difference is we go the other way. So now what's BF going to print? Remember, when we printed BE, it was 6. Now shift the other way, what'll it be? 6, 0. Right? So now the 6 will be shifted over by 4 bits. That's like multiplying by 16, 2 to the 4. Cool, right? Now suppose you want to make it say 6, 3. What do? I want to put a 3 in the least significant 8-bit, least significant 4 bits.
Or it with 3.
Yeah, or you can OR it with 3. Let's see now. CD byte EFG BG equals byte of BF or 0x03. And now when I print, can I just paste? Yeah. I could put out BG. And so now it should say 6, 3. And it does. So, you've all become exposed now to the wonders of bitwise operations in Java. Bitwise operations in action. You're all experts now, right? I'm not hearing a yes. But I didn't hear a no either. Suppose I wanted to take the bits and reverse them. Ooh. Why would I want to reverse the bits? That's a good question. Why would somebody want to reverse the bits? They flip them, right? So the least significant bits become the most significant bits, and the most significant bits become the least significant bits? Why? Why would you do that? Believe it or not, in my youth, when I was your age, I used to write device drivers, and the device drivers would allow me to interface mainframes like IBM mainframes to mini computers like Digital Equipment Corporation mini computers. That company no longer exists. Well, turns out there was a device access control unit which would interface to a proprietary IBM channel and a Digital Equipment Corporation unibus, which was a very specialized bus that only DEC had. And channel was another specialized bus that only IBM had. And they installed the dual inline package switches backwards. So you had to flip the bits around. That's pretty exotic. There's another reason to flip the bits. It's part of a fast Fourier transform. Whenever you do an FFT, you've got to flip the bits around. This is how they do the butterflies when they do what's called the Radix 2 FFT. Are there other reasons you might want to flip the bit? Yes. Two kinds of ordering for binary vectors. One is called Big Endian, and the other is called Little Endian. Big Endian refers to the IBM mainframe, and Little Endian refers to everybody else, all the microcontrollers. So when you want to convert from one computer to the other, you've got to do the bit reversals. So here is a way to do bit reversals. We're shifting over to the left by 1, and then we take the least significant bit and we grab it, mask it with a 1, and then add it into the answer. Then we take the entire vector j and we shift it over to the right by 1. And then we repeat, and we do it 32 times. So what we're doing is we're grabbing the least significant bit with a mask, and then we shift to the right. And that does a bit flip. Want to see bit R in action? What we'll do, let's see if, actually I'm not sure what test bit R does, so let's try it. It's been a while. Yeah, that actually worked, oddly enough. Here it's 1101010, and if you read this backwards, 01101010. It's the same thing backwards as it is forwards after the flip. That's pretty cool, actually. Bit reversal. Let's see, we did, here's a char example. Oh yeah, char. Let's see what happens when you use different chars. Yeah, so here's different characters. These characters are mapping numbers directly into displayable ASCII text. Pretty cool, right? So what have we done? We took the numbers 0 through 128 and we mapped them into characters. What would happen if we took those numbers and we scrambled them with an exclusive OR operation? 0x, let's see now, 1, 1, and end paren. I think that works. Let's try it. So now instead of going A, B, C, D, E, it's giving us weird answers. And so what that means to me is I can encode my text, and then I can undo the exclusive OR operation by doing it twice. And so if I know the exclusive OR operation, I can scramble my text by exclusive ORing with it, transmit the encoded text, or what I will call the ciphertext, then I can decrypt the text by doing the exclusive OR again. And so I can encode and decode and make my transmission unreadable to the casual observer. Cool, right? How do I know that an exclusive OR again will decode it? Well, we can try it. Let's see if it works. 0x11, and then we'll do the exclusive OR. So this will exclusive OR and then exclusive OR again. That should undo it. Let's see if that's true. Did I forget to convert it to a char? I gotta wrap it with another. There we go. Run. Yep, and now it's back. So you can extract the numeric sequence back by doing an exclusive OR twice. So inside we have the, I'll call it ciphertext, and then outside we'll have what's called the plain text. And so what this means to me is I can take strings and I can develop a simple encryption algorithm based on exclusive OR. What's so funny? Are you marveling at the wondrousness of bitwise operations? More or less. So let's assume for the moment that you want to take my new algorithm for encryption. We should give it a name, right? Doug's dumb encryption algorithm? Ooh, I like it. But we should encode the name, right? Let's call it algorithm DDEA for Doug's dumb encryption algorithm. So this will be algorithm DDEA 1.0. That's a good name, right? You don't like my name? I like my name. I think it's very nice. So now what we'll do is write a subroutine, public static void. I guess it has to return something or other. Let's have it return some encoded string, and we'll call it encode. Encode. And we'll pass a string in, s, and we'll return a string. Let's call it encoded. And let's have another one called decode. Public static string decode. 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 And it will take in a string, which would be, I guess we would call it encrypted text or ciphertext, CT. The input string here will be plain text, PT. And then what we'll do with encrypted text or ciphertext is we'll return plain text. And this will be return plain text. Whereas this will return cipher text. Right? So now using my algorithm, and we can make this into a little homework assignment, use your main method to print encoded and then decoded text. So what we'll do is we'll have a string that's called, I'll call it the plain text.
Spell plain wrong.
Plain text. Plain text equals, end quote. This is unencoded, or decoded if you prefer. And then what we'll do is we'll say S out, Control J, enter. We'll print out the decode. No, we want to print out the encoded of the plain text. And then what we'll do is we'll do S out, Control J, enter, and we'll go decode the encode of the plain text. So that'll be the inverse operation. And I gotta write encode properly. E-N-C-O-D-E. There. And so now your job, should you decide to accept it, is to write the implementation for this program using my algorithm DDEA version 1.0. Doug's dumb encryption algorithm. And what we'll do with Doug's dumb encryption algorithm is we'll bring up Blackboard. Oops. Oops. And we'll turn it into a homework assignment. Biomedical imaging. Which one should I use? These.
That's a signal processing.
Oh, that's a signal processing. Oh, that's weird. That's still in there. So now we do course content, assignments, add an assignment. Let's call it homework 2. And we'll call it bitwise ops. Bitwise ops. And we'll say implement the encode and decode for the following code. That's a little too much code, huh? Paste. And then what we'll do is grading is 100. And then allow unlimited attempts and make it due in a week. and make it do at 5. And what do you think of that?
So what's left for us?
You have to implement the this decode didn't properly decode the text, and the encode didn't properly encode the text. It's just samples. So you got to actually do this.
So you would like us to use your algorithm of XORing?
Yeah, or using XOR. I guess I wasn't clear. Implement the encode and decode for the following code using algorithm. All God's children got algorithm. DDE. Doug's dumb encryption algorithm. Is that it? Version 1.0. 0.3. Oh. And
The algorithm in the code.
yeah, well, you can see what it is.
Yeah, okay.
It's this. I don't know if I can scroll down in Blackboard, but it uses to encrypt a single character. You'll have to exclusive OR the character one character at a time in the string. So that means you'll have to turn the string into an array of char, then iterate through the char, doing the exclusive OR operation, and then reassemble the array of char into a string. You might be able to do it with a string buffer, but I'm not sure. I haven't tried that. I don't know that that's any easier than just converting a string into an array of char. Any other questions before I hit submit? Ready, set, go. Ta-da! Bitwise ops. They're like special ops. Ooh, special ops. So there it is. It's like a homework. Now, this class goes from 5 to 7:30. So we still have a little time. Huh? But we can stop.
I'm kidding.
But we could stop. Yes, it's true. But anyway, we got through the ops, and I thought that was pretty good. I'm glad we did that. And so now you know more about ops than you ever knew before. Yes, sir.
Are they going to come to play?
Are the ops going to come to play?
Are bitwise operators going to be significant?
Oh, yeah.
Like
Oh, Professor Lyon, are we actually going to use all these things that we just learned? Yes. Yes, we are.
Yeah, that's it.
We're using it for the image processing because you have to use them to pack your pixels. So all your data types are going to be packed, efficient data types. And you'll be packing and unpacking all the time. That means that a single 32-bit quantity is going to contain multiple colors, right? So it'll be red, green, and blue plus an alpha color plane all packed into a single pixel.
Oh, yeah. Could you say what the alpha factor does?
It's overlay. So what it does is it blots out areas in the screen so that you can put in annotations like text.
So, how does it interact with the 3 colors that you gave me?
It can blot them all out equally.
It's only used if you choose to use it.
Yeah, you don't have to use your overlay plane, but in general, Java requires that it exists.
So it's like on top of.
Yeah, you can set the overlay plane so that it passes all the colors transparently. But in general, it's a requirement in Java that it appear. The Abstract Window Toolkit insists on it. So here's anding and oring. We know about these things. Let's see. What is left to say about bitwise ops? X. I guess this is too much junk. This is base number conversion. You all know about this stuff, right? Binary, base 8, base 10, hexadecimal. In Java, if you want to output in binary, you can use integer.toString and specify the radix as 2. If you want to output in octal, you can use integer.toString and specify the radix as 8. You can go all the way up to 36. I don't know why they stopped at 36, because base 64 is very important. Why?
Power two.
Well, aside from the fact that it's a power of 2.
It's like a common architecture.
It's used in MIME encoding. So when you base 64 encode your binary data, you can pass it through a mail transfer agent because it will look as though it is text. But in fact, what it is really doing is it's taking binary data, encoding it efficiently as character data, so the mail transfer data agent can pass your attachment through the mail. So when you attach an Excel spreadsheet, the mail transfer agent says, well, I only pass text. So you encode, or base 64 encode the binary data so that it can come in as a text attachment, go through the mail transfer agents, and then be reassembled at the other end. So MIME stands for Multi-Purpose Internet Mail Encapsulation. And so what that does is it allows you to use standard mail transfer agents and transmit binary data. Send an attached image. Send a Word document. So MIME is so important for transmitting binary data so that it looks like text. Why do they call it base 2? Yes, sir. Go ahead.
I was going to ask, does that explain like the limit to like attachment sizes?
No.
Is that
No, your attachments, you can make a base 64 document as large as you like, in theory. If they are limiting the attachment sizes, it's because the mail transfer agents can't handle it. There may be practical reasons why you wouldn't want giant emails to have to be downloaded every time you go to visit your POP server. Because in general, if you said to me, well, I'm going to email Doug a 64 gigabyte file, and he can't read any of his mail until he downloads my attachment. Ah ha ha. Well, that's a denial of service attack, right? That wouldn't be good. And it would be especially onerous if you emailed it to your 5,438 closest friends, right? Because you'd be choking the entire email system. Imagine if I did that to my Yahoo group with Inventus. I'm the president of the Inventors Association of Connecticut, and I have 5,000 plus people on my email list and my Yahoo group. Right? Wouldn't it be sweet if I sent them all a giant attachment, like a 64 gigabyte attachment? Right? That's like the size of a small city. Can you imagine? It would be a crowd of angry peasants carrying torches, burning me in effigy. But on the positive side, whenever they burn you in effigy, it really doesn't look very much like you.
So what stops you from doing that?
Well, the mail transfer agents have these limits on how much you can actually send as an attachment. Also, I don't think the Yahoo group facility allows you to send attachments, but if it did, it would have to limit them. On the other hand, I'm a Java programmer. And what that means to me is I can write a Java program that sends an email attachment. And it can read through a long list of email addresses and send an email attachment one after the other. So in theory, if I were a bad actor on the internet, and I'm not recommending that you do this, I could write a program that essentially chokes the mail transfer agents and does a denial of service attack. But don't you do that. because that's bad. And if they find out you did it, I'm going on record telling you that's not something you should do. But here, let me show you how. So there's this program, and it's over here in the network package, and you shouldn't do this, okay? Don't do this. And it's in the mail package, and it will allow you to use your mail server of choice, be it Yahoo Mail or Gmail. And yeah, it could look like it's from you, but if you run this application as a fully vetted, trusted Java Web Start application, it'll look like anybody who's running your application from their client, so it'll look like it originated from them. But don't do that. No, what you could do is you could put it up on your web page, and anybody who visits your web page and runs your application could then send this email, because it would be a trusted application, and it could send it to an arbitrary POP server. So in effect, you could have a Java Web Start application that looks like it sends death threats to the president from somebody else's machine. And that's a felony, and you shouldn't do that, because felonies are bad. But here's how you would do it. So effectively what you're doing is you're writing an email client, and the email client goes out to the machine of your choice, in this case Gmail, and then proceeds to start to send emails through the Gmail client. And then you could choke the mail transfer agent with giant UU encoded attachments, or send interesting emails to interesting people. Did I mention you shouldn't do that? Don't do that. Yeah. Professor Lyon told me I should do that. And you can imagine what would happen, right? You get a knock on the door, and it's the Secret Service, and they said, I understand you don't like the president. You'll say, oh, but I think he's just fine. What's the problem? And you say, well, you've been sending these very angry-looking letters to the White House, and these death threats, and we don't think that's correct. Oh, no, it wasn't me. Well, it came from your machine, and we have your IP address. Wow, they got you. It might take a while. Those guys are smart. They'll probably figure out it was my lecture. Why do they call it base 2 anyway? Power of 2. Yeah, because in positional notation, 2 is used in the base. Right? 2 is used in the base, and you raise it to a power based on its position in the vector. That's why they call it base 2. And if it was base 8, then the base and the exponent would be 8 in positional notation. Right? So, do we need to review arrays? I don't think so. Let me just make sure. Row major versus column major. Arrays are so important in image processing because images are arrays of pixels. That makes sense. And if you have an array, a two-dimensional array, you want to address one pixel so that it's adjacent in memory to the next pixel. That makes sense because you don't want to jump around in memory, because if you jump around in memory, what will happen is you'll lose what's called memory coherence. What's memory coherence? When you cache, right? What's a cache? Caching inside of CPU, what's cache memory? It's memory which is internal to the CPU chip, versus like the RAM that you run out and buy for your the Sims that you put into the computer. A CPU has its own memory, and what it does is it goes through a 4-stage process. It fetches the instruction, it decodes the instruction, it executes the instruction, and then it stores the result. That's a four-stage pipeline. So in a four-stage parallel pipeline, you get all four of these things happening at the same time. While one stage is retrieving an instruction, the next stage is decoding the instruction, the next stage is executing the instruction, and the fourth and final stage is storing the data back. So those things can all happen in a single clock cycle in a superscalar processor. Well, as it happens, there's also a way in which you can speculatively prefetch the memory from main memory into the internal, very efficient, very fast cache memory of the CPU. But that only works if you're accessing the memory sequentially, which means you have to have memory coherence. Well, in order to be able to access memory sequentially, that is, go from one address to the next address so the two addresses are adjacent, then when you move from one pixel to the next pixel, you have to make it sure that those pixels are stored in adjacent areas in memory. But you have a two-dimensional array. And the two-dimensional array is being accessed through a doubly nested for loop, as you can see here in the example. So how do I know? How do I know if I'm accessing the array pixels sequentially in memory? It looks to me like I have I as my row and J as my column. And the thing that's incrementing more frequently is J. So I'm going down the column, right? No, across the column, sorry, and then going to the next row. So I go across the row, and then across the columns, across the columns, and then down one row, then across the columns, and down another row, right? That's how that works. So then the question is, if I go across the columns, am I addressing pixels sequentially in memory? Am I having memory coherence? Because if I'm not, it's going to hurt my performance in my CPU a lot. I mean, really, big time. Every single pixel access will be a cache miss, because that pixel will not be in cache. It won't be in the fast memory inside the CPU. So how do I know if I should access columns first or if I should access rows first? Should I have J execute more frequently than I, or I execute more frequently than J? It's just a matter of inverting the I and the J in this operation that I've printed. How do I know which way is most optimal in terms of the CPU's performance? How do you know? It's a trick question. You don't know. It's not a part of the Java language specification. They won't tell you which way arrays are stored, whether they're column major or row major. If they're column major, you want to go columns first, and that's the way this is written. If it's row major, you want to go rows first. In Fortran, it's row major. In C, it's column major. In Java, they don't tell you. Wow. Well, they don't tell you. You can figure it out by test benchmarking it. So if you benchmark it on your virtual machine, you can figure it out. Or you can simulate two-dimensional arrays with one-dimensional arrays using a multiply and an add. So if you use a multiply and an add, you can add the columns and then multiply by the row number and the number of elements in a row. Well, this is, kind of a big problem.
That searches the whole column first and then the row?
Yeah, this goes across the column, and then it goes to the next row, and then goes across the column. I will be held as 0, and then J goes from 0 to A of 0 dot length.
Is J the column or is J the row?
Yeah, it's first row and then column. So it's RC. So I'm making I is the row and then J is the column.
Didn't that search the whole column and then move over a row?
Yeah, this goes across all the J's and then goes to the next I. So it's column major. That's the way this was written. If it was row major, then it would go across all the rows and then go to the next column. So this is written in row major form. So here's how you increment. The array in the top is written out with all of the rows and columns. 0, 0, 0, 1. That's row 0, column 0. Next element is row 0, column 1. Then row 0, column 2. And I'm reading the array in column major format. And that's how it goes down in here. These are the indices if you go row major versus column major. So you have to know, if you want to make your code really efficient, how your two-dimensional arrays are being stored. Or you can simulate the 2D arrays. You can get an x and y location by using a multiply and an add. Now it turns out multiply and add is a single assembler language instruction, which you can find in most modern 32-bit RISC machines, multiply add. So it takes only a single CPU cycle. And I see this a lot in Java. That way you'll always know how the order in which things are running. In this case, I'd want x to be incremented more rapidly than y. Right? That way I can be assured that I'll be accessing pixels in a memory coherent fashion. And then comes this section on drawing in Java, which is a completely different topic. So then the question becomes, how do you know what the underlying result will be if you go from row major to column major without trying to simulate two-dimensional arrays? And the answer is you have to benchmark. That's the only way to know for sure. And I think it's a really unfortunate part of the Java language specification that they didn't specify whether they were storing arrays in row major or column major format. What do you think of that? It's a limit. It's a limit of the language. They should have told us, but they didn't. And they didn't make it a spec. I'm not going to get into this drawing thing right now because I think I've gone a little too far, too fast. What do you guys think about this row major, column major thing? Do you think you could tell which one's faster? You know how to do the benchmarking? Yeah, use a timer, sit down, write some code. Do you suppose anyone could have done this kind of benchmarking already? Somebody. Who could have done such a thing? Somebody who writes image processing programs might have done that. Somebody who shall remain nameless. Let's see. Did I do it? I might not have done it. I think I did it, though. It sounds like something I should have done. Doesn't that sound like something I should have done? Here's an array that sets the main diagonal. That's pretty trivial. How about two-dimensional matrices? There should be a way to show members, right? Show members. There we go. Now, how would we know? Well, here's something where we're taking a two-dimensional float and we're adding an integer. It looks to me like somebody has decided it's column major, because the columns are going more frequently than the rows. Don't see any benchmarking, though. Well, I think it would be too tedious for me to do this in class right now.
Stack Overflow is a really interesting answer.
What's the answer?
Either.
It's neither column major or row major?
Yeah.
Because they didn't put it in the language specification.
Okay.
That you can sit.
Apparently Java doesn't have multi-dimensional arrays.
It just doesn't have them.
It has arrays of arrays.
Arrays of arrays.
So should be like fine.
Yeah, you know what? I think just because somebody printed it on the web doesn't necessarily make it true.
Got 19 hours.
Oh, well, there you go.
20 people. It says it's probably a row major.
Probably row major?
Probably.
Probably?
It's saying it's probably more efficient to go row major.
Probably? Don't you think someone should benchmark it rather than make a conjecture? Yeah, I don't understand why. I mean, first of all, if I found one that was row major as a virtual machine implementation, do you think maybe I could find one that's not? You betcha. So every virtual machine has the potential to be different. So this is a big problem. That means you can't write portable, optimized array, two-dimensional array code. Big problem. So drawing in Java, I think it's probably worthwhile mentioning that you can draw images in Java, you can draw other things in Java other than images. There's a native windowing system. It senses damage, and the damage control manager is responsible for repairing that damage with paint invocations in specific areas. It knows which areas have been damaged because it senses when windows are being dragged around. So when a window, a rectangle, is dragged around, and windows are almost always rectangular, then they cause damage in certain areas, and the damage control manager runs in the background as a thread inside of the Java virtual machine and calls repaint on certain areas. So as you repaint certain areas of the image, you should expect, and you are entitled to expect, that you don't have to repaint the entire screen. It only has to repaint the area that's been damaged. So when there's a pop-down choice menu that appears on your screen, in general you would expect that when the pop-down choice menu disappears, only the area underneath has to be repainted. That's what you would expect. That's a reasonable expectation. That assumes the damage control manager knows the abstract window toolkit's damage. It assumes you're using the abstract window toolkit. That assumption is without foundation, because you don't necessarily have to use the abstract window toolkit in order to have a graphic user interface. You can use the SWT, which Eclipse uses. You could use swing. You could use heavyweight native methods for doing your drawing. And some of those include Java 3D. So if you want to mix swing with Java 3D, you can fool the damage control manager and not properly update the screen. So this is one of those fallible things that was built on a series of assumptions that are no longer necessarily true. So you have to be very careful about how you mix swing with the native Windows system of Java 3D, for example. And if you inadvertently mix swing with AWT, then in effect you'll have lightweight versus heavyweight drawing on your screen, and the damage control manager can't be responsible for keeping things looking clean. So this damage control manager can play a lot of tricks on you. Has anybody here ever done any serious swing programming? Graphic user interface programming? No? Kyle?
I just made like a dialog box. I don't know.
You made a dialog box. Okay, that's good.
And like buttons.
How many people have made a dialog box?
I don't know if it was swing or not.
Okay. Like a file open dialog box? You should have done that. Yeah, you've done that. Sure. So, well, I'm not going to get into that now. I think if I do, it'll harm my ability to, discuss these things more abstractly. So I've got I don't know, what do we call it? A toolkit. I think that's the term. Toolkit is not a design pattern. A toolkit is just a collection of a bunch of related things that help you solve a particular kind of task. And my toolkit for image processing resides in a series of static methods that are inside of a class. Anybody know what the class is named? I think we discussed it last week, didn't we? It's called image utils. So image utils lets you display an image. And so image utils lets you do a whole bunch of operations. And you call image utils dot, and you can invoke a whole bunch of methods which do image processing. So here's a little image frame, and that's part of some toolkit which actually stores a whole bunch of two-dimensional arrays for red, green, and blue, and lets you set an image and get an image. These are all parts of things that you could get from other places as well, but I like the idea that you can just open a GIF image and then display it. And in fact, I think we saw that as an example in our last class. And probably you tried it yourselves, right? Didn't we do a little example last week where we displayed an image and showed it? I thought we did. Let's see now. Here, display image. What does this do? It's been so long. I don't think this will still work. This wants to use a URL as the source of your image. I'm convinced that this won't work, but I will try it anyway. Let's take the URL here. What did I do wrong? Oh, missing a quote? Ah, that's better. Tell you what. Let's do something from scratch. I think that's better. Let's do new Java class, and we'll call it simple. Oh, I know. Display image file. How's that? Okay, so you guys tell me. You're now experts. How do I do this? Image img equals Alt Enter. What do I do? Do what now? Equals image utils. Help me out. Get buffered image. And it says here I need an image file. Alt Enter. And I guess it'll be something like futils dot get read file, and we'll select an image. End quote, end paren, sem. Did I miss a parenthesis? Alt Enter. It looks like I've got a wrong parenthesis somewhere. Get buffered image. That's better. And so now I got to display the image. Image utils dot display image, and then put in the image and something else. Quote. This is an image. Sort of a dumb name. Probably ought to put the image file in there. But that's okay, because I'm too lazy. So that should display an image. Using little more than image utils. And here's an airplane. and there's an image. Good deal, right? So we sort of did this last time. Well now, suppose I had image utils in here. Get image, and it says here I've got a whole bunch of choices. I do Control P to get the choices. And here's a display image from before, and it says here I can get an image from an arbitrary URL. An arbitrary URL, and I get the URL by saying new URL, and I pass in a string. So what that means to me, the user, is that I can put in an arbitrary URL, get a string, and then make an image off of that URL. So then the question is, what string should I use? He's giving me a hard time because this could be a bad URL. So let's throw that in the list of exceptions that the main can throw. So I need a URL for an image. You guys got one? URL for an image? Let's find one. I'll use Java. Oh, I know. Let's use Google. Right, Google is good at that. Let's find, pick a topic. ENIAC. I like it. ENIAC. ENIAC. And then what we'll do is we'll click on Images. And here's a nice image of ENIAC. And what we'll do is we'll view the image. And there is an image that came in off of the web. So what we'll do is we'll grab that image and paste it right in there. So that is a JPEG image of computing history. We'll get the image, and then what we'll do is we will display the image. I'll use IMG for that, and I'll comment this stuff out. Here, how's that? So I got a ENIAC image. I got it off a URL, and then I'll display it. What do you think of that? That sort of looks like code, right? Very code-like. Oh, that sort of works. It's an ENIAC image I snarfed off the web. That's a real nice ENIAC image, actually. You can really see the program. It's programming the ENIAC. You don't store the program in RAM. You store it in the plug board. I don't know. That's a very good question. I assume they can handle substantial current because ENIAC used 18,000 tubes. It didn't have any transistors, you know. Yeah, well, they look very thick, actually, compared to this woman's arm. I mean, look at these things. These are substantial power cables. I never noticed that before. These are huge. ENIAC. So now, suppose we wanted to take that image and zoom out. What could we do to zoom out that image? Do what now? Can I do that? Nope. I gotta scale the image. So let's take image, and set it equal to image utils dot scale, maybe scale fast, scale image. I'll scale it to a width and height. So I'll take the image and I'll scale it so that it's 800 by 600. N paren sem. And now maybe it'll fill the screen. Maybe. And it does. Now I think I recognize this woman. Anybody know who that is? No, that's Rear Admiral Grace Hopper. Oh yeah, she's the woman who had kept a notebook, and what happened with the heat from the ENIAC, since they didn't have air conditioning, is they had to open up all the windows, and because of the light, the moths would come in. And the moths came in and they got into the machine because they were attracted by the light, and they messed it all up. So she took one of the moths out and she used some scotch tape and she pasted it into her notebook, and she said, "I found a bug in the machine." And she's the person who coined the term bug. And that's why we debug programs, because of Admiral Hopper. No, you had to open the windows. These things drew as much power as a city. They had a whole floor of power supplies. Admiral Hopper. Isn't that her? I thought, yep, that's her. Here she is. Same. I recognized her immediately from the glasses. I don't think she changed her glasses. Same woman. Amazing Grace. Worked on the Mark IV. I worked on the ENIAC. I'm pretty sure that's her. And I don't know if they have any pictures of her when she was young. Yeah, there she is. Same woman. Isn't that the same woman? In the same profile? You tell me. I don't know if I can get the Java program to show both images at the same time side by side, but I'll bet you. Isn't that her? Pretty close. That's Admiral Hopper. How about that? So that's what I have for you today. My Java program discovered Admiral Hopper programming the ENIAC in 1944, it must have been. World War II was over in December of 44, and the ENIAC was constructed so that it could model implosions for John von Neumann, who worked over at the Institute of Advanced Studies at Princeton. He ran into Colonel Goldstone at the train station in Princeton, and Goldstone was telling John von Neumann about this machine, and von Neumann became very interested in it because he had these classified problems that he was working on, and he thought he could find a good application for it. The Ballistic Research Laboratory initially had funded the ENIAC in order to be able to do artillery tables efficiently. So it was never intended to do implosion simulations. John von Neumann went on to build the ENIAC into what would be called the von Neumann architecture machine, which he termed the EDSAC, which is a slightly different computer because it had a stored memory for programs. ENIAC didn't have that. But ENIAC was really the first general-purpose electronic digital computing system. And Grace Hopper worked on it. So that's what I have for you today. You've got a homework assignment. Enjoy the rest of the evening and the weekend.